Hi, and welcome to the first EVPM podcast. I was fortunate enough to be joined by EV motor specialist Antti Lehikoinen, and we discuss mostly the new Tesla Model S Plaid carbon wrap motor, and then in the later parts we go into electric aviation. Unfortunately, during this podcast, my audio cut off, so I will be adding the questions I asked him after the fact, so there might be some things that are out of sync. The format is a Zoom call. I'm hoping this format will stay for the other podcasts. So let me know what improvements we can make or what you want from future podcasts. So thank you. Those are the few brief words from me. Enjoy the show. So here I ask Antti to talk a little bit about himself.
Yes, sure. So, hi, my name is Antti Lehikoinen, Antti for short. And I run a consulting business called SMEKLAB Limited that does design on electric motors and optimization and so on. And I have been doing this for about 4.5 years now, since 2017. The first few years were strictly part-time because I was still finishing my PhD and working as a postdoc in Aalto University, Finland. But since about 2.5 years now, it's been closer to full-time business. I say closer because I'm still involved in 2 startups here that take some percentage of my time, but other than that I'm strictly a motor designer, and I have been lucky enough to work on a very wide range of projects, from high-speed industrial machines into EVs, e-bikes, e-trucks, and even into aviation like electric airplanes. So I have been extremely lucky in that sense, so I have been able to test my skills on wildly different topics. So I know a bit about everything and not too much about anything. Jack of all trades in the motors scene, basically.
So how did you get started with your own consulting company?
That's a good question, actually. I was thinking that I could do it for a long time. I was like semi-open to it, but I didn't like actively pursue it. Then about early 2016 I started my blog writing on finite element analysis, which was the focus of my PhD studies, then some general engineering motors stuff. Until finally I was contacted by a prospective client that needed my help on something, and they were very eager for it, and they needed my help. So I thought, okay, well, this is a great time. I set up my own business here, which is luckily a quite simple process. You just fill an online application and open a bank account and deposit a small amount of initial capital. It used to be like 20,000 euros earlier, but it's been reduced significantly since that, so it was not a big financial risk or anything. So yeah, that's how I got started, and ever since I have been lucky enough to get a steady stream of clients, both old and new. And they usually find me by word of mouth or by spotting me online, by Googling, by LinkedIn, stuff like that.
Do you work by yourself or have you employed someone?
Yeah, it's a solo business for now. I have worked together with other consultants occasionally, but most of the time it's just me.
Could you tell us a little bit more about finite element analysis?
Okay, so finite element analysis is analysis itself is a mathematical technique, but in practice it means that you are using a software that is doing finite element analysis underneath the hood, and you use the software to analyze the behavior of a motor, let's say. That's how I use it. So you basically, within the software, you make the geometry of the motor. You tell it what kind of materials you have, how the outer coils, everything are arranged. And then you simulate it, run the analysis, and you get some results out of it. Usually you want stuff like torque or power that the motor is producing, auto losses, which you need for, well, efficiency is what most lay people think is the most important thing. Additionally, you need the losses and distribution of losses for thermal analysis, making sure that the motor doesn't overheat, stuff like that.
What can you learn from an analysis like this?
Okay, it depends on what you focus on and what you actually care about. When it comes to engineering softwares and engineering fields, motors are luckily quite easy to analyze. It's like the physics, the mathematical basics, they are quite well understood, and then the analysis is not too difficult. Computationally speaking, it doesn't take that long. It's not like CFD, like fluid dynamics, which is, as far as I know, much more complex. Motors are quite easy in that sense, and usually you can get a very good agreement between most of the results. Like the torque or power usually matches within 10 or 5 or even 2%. The total losses, or the efficiency will be close. Usually the software predicts a bit higher efficiency than what you can actually reach. And one of the biggest reasons is that the losses in the iron components, the magnetic iron in the machine, they are hard. They are still hard to predict. That's maybe the single hardest thing. Nobody really trusts the iron loss figures that they get. And usually the people simply include some kind of a safety factor of 1.5 or 2 there, stuff like that. But luckily in many machines, especially if you think of high power density machines, the iron losses are a relatively small part. Well, they are not ever small, they are usually between 10 and 50% of the total losses, so they are significant indeed, but there are still other components.
In school, I learned a lot about the equivalent circuit. Do you do any analysis on those?
Yes, I do occasionally work on them. Like many people, many customers, clients, they do want the equivalent circuit of the machine. So of course I compute lots of them. And using the circuit, the motor is also easier to analyze. Like for instance, you want to simulate the machine at a certain operating point, meaning a certain power and a certain speed. And for that you will have to decide how you are gonna be supply it. Like what kind of voltage or current you are gonna be injecting into it. And the equivalent circuit is an awesome tool for roughly determining that value. It's not gonna be perfectly accurate ever, but it can be quite good enough.
Does the air friction in the motor itself impact the operation in any way?
Oh yes, there are. Well, it depends on the machine, how significant they are. If you think about typical industrial motor, let's say that you could find in the garage of your father or grandfather driving some bandsaw or something, it's gonna be like this big and weigh 100 kilograms and output 1 horsepower or stuff. In that kind of industrial machines, especially the old ones, the air friction, or we call it windage, the windage losses, they are usually quite non-significant. On the other hand, if you go to high-speed compressors that might be spinning at 30,000, 60,000 RPM, even up to 200,000, nowadays I think many people are going. In that kind of speed, the windage losses, they can be easily the biggest single loss component there is. And that is indeed a difficult phenomenon if you wanna model it very accurately, because you are gonna be having all kinds of nasty turbulence and so on. I have never done it myself. I simply use some good old engineering equations to get some idea of the magnitude of those losses.
So I have this picture here of Jean-Marc. If you haven't seen his art, you should probably check it out. It's pretty interesting. It's an vision of what the future would be like. We can see here the year 2000. And in this example, he envisioned children learning through this electrical wire that is hooked up to this device, which basically just churns books into knowledge that is then, sent through the wires. So this made me think about Neuralink and neural interfaces. That seems like a very difficult problem to solve, and maybe all hope lies in the fact that the electrical signals are wireless, then you might be able to pick them up. What do you think about that?
Well, personally, disclaimer, I know absolutely nothing about the science behind, but my impression is that it's not gonna be working anytime soon. Humans are far too complex. I mean, one example I like to always make is that when you work in an electrical engineering lab, you have a big box of electronics that costs like $10,000. You use that to input 5 volts of sine wave. Then you use another box, maybe worth $50,000, $20,000. You put it right next to it and you measure. And you should be outputting 5 volts, and you are usually measuring like 5.1 or so. And then you have to spend 2 days debugging to see what's going wrong. So if you contrast that, like a very simple measurement using very expensive high-end equipment and a very simple system that should work, and you compare that to humans, which are infinitely complex, and then people are using all kinds of smart rings or smartphone apps and whatnot, watches, and they are supposed to tell you something about the state of your health or stuff. I don't trust that at all. And likewise for, having a neural interface would be like, I don't know, 6 orders of magnitude more complex than that. I mean, they have had some hamster trials or so that may have shown some promising results, but for now I'm not very enthusiastic. I don't expect to see any real life usages anytime soon. I sincerely hope I'm wrong, but that's just my feeling. Okay, you should be able to see it now. Okay, so the Tesla Model S blade motor, generally marketed as carbon-wrapped motor. Okay, like often with Tesla and the surrounding news reporting, things have been very confusing to people who actually work on motors. So lots of confusion here. So right now what it seems that what they have is seen in this kind of a teardown picture here. So the rotor of the machine, it's wrapped inside a carbon fiber sleeve, which is the black thing here. So it's like a bandage made out of carbon fiber. And why it's there and why it does what it does, maybe it's the easiest to understand when we look at the typical structure of an EVPM, so an interior permanent magnet machine. So what you see here is part of the cross-section of the motor, and the rotor is here on the inside. And the magnets, like the name says they are interior, they are inside the rotor, because well, it's easier to protect them. Somehow you can reduce the magnet mass required for the machine. They are maybe easier to manage thermally, so on. You can reach higher speeds and so on. But anyways, what the typical structure looks like is seen here. So the magnets are this in some kind of a V shape. Many companies also include a third magnet here in the middle. But what always, until now, what they have are these kind of a thin bridges of iron between the magnets, because well, you simply need to have them to hold the pole piece, the center lump of iron here in place. And when you have these kind of bridges, what happens is that when you look at how the flux lines, how the magnetic flux or flux density is going, is that you have some of the flux escaping through these bridges here. So some of the useful flux, I mean, ideally you would have all the flux going into the stator here, where it can do its job to produce torque, produce power. But some of the flux will be escaping through the bridges here. And for that reason they should be as thin as possible. But then you run into a conflict with the mechanical requirements, because the rotor is gonna be spinning fast, usually between 10 and 20,000 RPM in traction motors, and the centrifugal forces, they are gonna be huge. So the bridges here, they will be stressed very badly, and they need to be thick enough to survive that loading. So what Tesla seems to have done is that they have got rid of the bridges altogether. Like if you see this point here, where you normally would have the center bridge, they don't. Also these surface bridges here, well, it's difficult to tell from this picture, but I think they might not have anything here either. So basically they have the magnets here, and then the pole piece is just floating on top of them. And to keep it from flying off, they have this carbon fiber ring here that's holding them in place. And ideally you could, and well, I guess they can eliminate this leakage flux altogether, which is a good thing. On the other hand, it seems that this sleeve here, it's rather thick. It might be between 2 or 3 millimeters here, which means that the air gap of the machine, like this gap here between the stator and the rotor, it's gonna be increased. There is an optimum length for any motor. Usually in traction machines you see like 1.2, 1.5 millimeters, so it's not awfully thin, but still the carbon fiber sleeve here means that the rotor, like the magnetic air gap, which is like the sum of the physical clearance between the sleeve and the stator surface and the sleeve itself, it's gonna be increased almost certainly. So you gain something in performance and you also lose something. But based on the specs that they have released of the Model S, well, they are quite convincing. It seems to be a very very high performance car, so the motors, they are most likely working very well. Yes, that's a good point. I think it might be a zero-sum game here, so that they don't really gain anything by that alone. They might even lose something, but what they also gain is that by having this carbon fiber sleeve here, which is mechanically very strong, they are able to spin the motor at much higher speeds. And when it comes to motors, usually higher speeds mean that you can extract higher power out of the same volume. So simply by having a mechanically more robust design and then increasing the speed, they can increase the performance of the machine by quite a significant factor. Yeah, well, alone it maybe doesn't translate into range, but if they can extract the same maximum power that they obviously want, if they can extract it out of a smaller machine, like a physically smaller size motor, then they can very well reduce the losses at lower, smaller powers, which is where you are gonna be operating the majority of the time anyways. If they can increase the efficiency in that range by having a smaller machine, then they can at the same time increase the range of the vehicle as well. Yeah, that should be checked. Usually these EV motors, they are not physically very big, about yay big, something like that. Yeah, and then when you factor in the cooling system, auto radiators and pumps and so on, it takes even more space. So, yeah, the motors alone, they are usually very compact and very power dense compared to combustion engines. Of course, then you have the inverter, the power electronics, and you also need some cooling, even for electric motors, but not nearly as much as you do for ICEs. Okay, then maybe another interesting aspect of the motor is how they make it, or how they make the carbon fiber sleeve. Usually this is not my expertise how they are actually manufactured, but as far as I know, there are two common ways to manufacture them. One is that you basically manufacture a long pipe of carbon fiber separately. So you make a hollow shell, very long, and then you cut it into pieces of suitable length and you press them, squeeze them on the rotor, or you push the rotor in. That is like the typical industrial approach with compressors and so on, because it's very suitable for series production. But the flip side is that the tolerances are usually gonna be bigger and so on. The other approach that I think Tesla is also using is that you take the rotor and you spin it and you wrap the carbon fiber around it. And that way you can like pre-stress it, meaning you spin the rotor and you stretch or pull the carbon fiber. It's like code when it comes out of when it's made. Anyways, you pre-stress it, meaning you can apply some compression on the rotor surface, like pre-compression, meaning it's mechanically more robust, it doesn't expand so much when it's spinning, so on. But on the manufacturing side, this is much more difficult because, well, you have to stress the fiber, you have to be able to attach it somewhere in the machine to be able to start spinning it, so on. And then you will have to probably cure it in an oven to make it rigid to end up with the finer sleeve here, that it's gonna be stay there and not simply unspool on its own. So yeah, it sounds like it would be tricky to manufacture in like series volumes, but it seems that Tesla, at least they claim that they have found a way to do that. Okay, again, this is not something that is my main expertise, but I think I remember reading that it is indeed tricky, these carbon fiber sleeves, especially in the vehicle application where the loading is highly cyclic, meaning it's gonna be highly loaded, it's gonna get hot, it's gonna cool down, hot, cool, all the time. And that is gonna be stressing, well, everything there, and especially the sleeve, because well, the one main drawback of carbon fiber is that it doesn't really expand when it gets hot. On the other hand, everything inside, the rotor, iron, the magnets, they do expand, meaning the rotor tries to get bigger while the carbon fiber sleeves tries to stop it from doing that. Meaning it will be very highly stressed when the machine is hot. So that's gonna be something to consider. And also, well, it's a composite, so it's laminated. There are these carbon fibers, then there's epoxy or some kind of a resin holding them together. And what can happen in the long run is that these layers of carbon fiber, remember it's spun and wrapped like that, so the carbon fiber is gonna be in layers, they can come loose from each other. So I hope and I think they have considered this and they have run some lifetime, like some kind of accelerated aging tests before actually publishing this information that hey, we are gonna be using carbon fiber from now on. Yeah, I think we pretty much covered the sleeve part here. And then the aging and reliability aspects. Well, one thing you have written down are common misconceptions about motors. And maybe the main thing here is that people are too focused on power. And yes, like there is a saying that electric motors, they don't produce power per se, they produce torque. Because how much torque a motor can produce, it is limited by physical aspects. It's like the strength of the magnetic field inside it, which is again limited by the iron. It has to go inside iron, and iron can only support up to 1.8 teslas or 2.2 teslas if you go with this very expensive cobalt alloys. Usually folks don't. So anyways, the flux density is limited, and then the other thing that is limited is how much current you can push into the machine, because that is limited by thermal reasons. You push too much, you simply can't cool it enough. So the end result is that for a certain size of the machine, the torque that you can get out is limited, and the only way to get more power out of it then is to either make it bigger or have it spin faster. And the spin faster approach is what almost everybody is doing. There's a very clear trend towards higher RPMs. So that's something to keep in mind, and it's a very common mistake that people make, like what non-motor people do. Like they need a motor for a certain application. They know that okay, I need let's say 2 kilowatts of power, and they need it at a very low RPM for a bike or something. Then they look up a catalog, see okay, there's a very nice small 2 kilowatt motor, and they fail to notice that it's designed for 8000 RPM, and it can produce 2 kilowatts at 8000 RPM or beyond. And they have a bike or some milling system or whatever that's gonna be spinning at 200 RPM. So they are not yes, you either need a much bigger motor physically, or you need a gearbox, or you can't get 2 kilowatts for that. Yeah, that brings me to another misconception. This is not something that lay people make. It's something that beginner engineers or engineers who don't know that much about motors is that they think that changing the turn count would help, like how many turns you have in a coil. Like, yes, yeah, they think that okay, I decrease the number of turns and the resistance gets smaller, you can get more power with the same losses. Unfortunately, no, it doesn't work that way. If you decrease the turns, you will have to push in more current by such a factor that you completely compensate for the reduced resistance, and you will end up getting exactly the same losses for the same power that you needed in the first place. So the turn count doesn't really influence the efficiency or power density at all. Yes, many people make that mistakes. Of course, there are some small practical effects, like what kind of insulation you need, how big your conductors need to be, how big your connection cables need to be, which is a huge thing if you are thinking of an application where the inverter is not right next to the motor. Yada yada yada, but as a first order approximation, the turn count doesn't matter at all when it comes to power. Yes, maybe one more thing related to this is what you have also written about the hype and reality of EV motors right now. Well, the hype question is easy to answer. What is maybe the most hyped right now are switched reluctance motors. There's lots of talk about them and lots of hype also. I wouldn't say unsubstantiated claims per se. I don't remember seeing any, but people are maybe putting far too hope on the technology, or at least far too much hype, because, well, it's been around for a long time. It has its issues. The motors, they are at least traditionally thought as noisy, and then it's very difficult to obtain the kind of power densities and efficiencies that you can get with permanent magnet machines. So they have a very tough competition against them. I'm not saying it can't work, it definitely can work, but simply non-motor specialists should be very careful about what they believe and what they expect of the future. But anyways, they are clearly the number one hype thing now. They have stolen the title from axial flux machines that were maybe the most hyped technology a few years ago. Okay, the thing with axial flux machines is that they can be a good fit for certain applications, but most people don't understand them at all. I want to tear my hair out when I read some of the claims or quote explanations about them. Like, yes, yeah. Like, what axial flux machines do well is that the average diameter of the air gap, like, well, there's this, what you see here is a radial flux machine, so the air gap diameter is simply the rotor diameter. And typically the larger your air gap diameter is, the higher torques you can produce. Because you can think of it this way, that torque is simply the force multiplied by the moment arm. Simple physics 101. And the moment arm gets bigger when your air gap diameter is bigger. And in the axial flux machine, axial flux configuration, the moment arm the average air gap diameter is quite big compared to the total size of the machine. So it's easier to produce higher torques out of them. Another thing is that you can make this kind of a sandwich machine, that you have the stator, the stationary part between two rotors, and with that configuration you can eliminate this back iron of the stator. It's the part of iron seen here, and as you can see it can be quite a large component, like its physical size, its mass can be quite large. You can eliminate that, so you save some mass there, some losses there. On the other hand, what you have on the flip side is where you have two rotors, twice the air gaps, twice the permanent magnets, so you gain some mass there. So yes, some benefits, some drawbacks. And like mentioned, axial flux machines, they can be a very good fit for certain applications. Naturally, when you need a machine that is shaped like a pancake, if it needs to be very short but can be wide, then okay, axial flux is a perfect fit there. For applications where the size or the shape is not constrained like that, I'm not awfully convinced. They can work, yes, but they are not the end-all best solution that some marketers and reporters have tried to make them to be, especially like 3 or 5 years ago. Now they are doing the same thing about switched reluctance machines, like I mentioned. So I wonder what's gonna be up in another 5 years or so. Maybe superconducting machines again. Yes. Yeah, well, if you think about electric aviation in general, it's a very wide field. Not so much has been built for now, mainly some small private planes, like you mentioned, but there are plans and projects going on all scales, basically. On the smallest scale you have these urban air taxis, which would be like the flying cars that you expected to have in the 60s, 70s. Again, if you look at those nice old atom punk pictures, you have flying cars there all over. Yes, indeed. Now finally we may have the technology for that. It's difficult, yes, but they could be coming. So that's the smallest scale. On the largest scale, people are speaking about this kind of a regional short to medium haul aircraft for some tens of passengers. Nobody is luckily yet speaking about fully electric intercontinental aircrafts like passenger jets, because, well, the technology is maybe not yet there. Well, yeah, you have those hydrogen fuel cell people, but let's not go into that yet. But anyways, the point is that people are speaking and designing electric aircraft for almost all scales that you can think of. And well, why they are doing that? Several reasons, of course. It's in now, so some folks are simply doing that to gather some investor money and then do something, gather some experience. But there are also some really valid reasons for it. The obvious one is that, well, folks are, well, there are the environmental aspects, of course. Okay, just a moment. Yeah, the environment is a big thing. Everybody is speaking about CO2 emissions, and for good reason. And aviation, unfortunately, is producing a rather large share of them. No, I don't have any hard numbers here. I would have to check it up, but it's a significant share. I don't know. It might be. There are like passenger planes, and then there's also this freight, like moving goods around. Yes. Yes. But yeah, anyways, like I mentioned that switching to electric planes would, of course, reduce the CO2 emissions by quite a lot. Not all of them, it depends on how the electricity is produced, of course, yada yada yada. It's a common counter argument against electrification that hey, you have to produce the electricity. Yes, but it's still cleaner most of the time. Yes. Yeah, with cars that is actually a huge benefit. Like even if they were CO2 neutral, you can eliminate the tailpipe emissions, which can be huge, especially in bigger cities, especially in bigger like developing world cities, where the air quality is just horrible. But again, if we return to aviation, so there is the CO2 benefit, then there is also the cost benefit. Because if you look at airline operators, where the money goes, the fuel is actually a very major part. Do I have some numbers? Yes, I think I remembered that Finnair, the Finnish airline company, is spending up to 20% of their money or costs is going on fuel. And if they were able to electrify their planes, of course they can't, not all of them, not with the current technology, but if they were with the current electricity prices, they would save lots and lots of money. And that's also the observation of all EV owners, that it's much cheaper to ride. Especially here in Finland, where gasoline is quite expensive, it's taxed heavily. So EVs are for now much cheaper. It's gonna be getting worse in the future, of course, because electricity prices are almost certainly going to go up. But still, I think for the foreseeable future, electrification is gonna be much cheaper. Yes, so that's why even planes are going electric. Now if we speak about what kind of planes could go electric, well, obviously batteries are the main limitation nowadays, like their energy density is way lower than what you have in gasoline. Yes. Okay, where the power goes is that... Okay, there are several things to consider. One main thing is that the biggest power consumption occurs when the plane is taking off. I think the takeoff power of a jetliner is usually like 3 or 5 times bigger than the kind of power that is consuming when it's cruising, when it has reached its final altitude and it's simply going forward at constant speed. So the takeoff power is huge. And that's where the majority of the energy is gonna be going. Or majority of the power, at least, and a significant part of the total energy it has to carry on board, like the fuel or the embedded energy in the batteries. And then of course when it's starting to coast down, preparing for landing, then it's very small what it's consuming. But anyways, if we speak about energy densities of batteries versus fuel, batteries like lithium ion, they have theoretically something like 300 watt hours per kilogram per cell on the battery level when you factor in all the cooling and battery management systems and so on. It's closer to 200 or so. Whereas jet fuel has 13,000. So there's like a 2 orders of magnitude difference in favor of jet fuel there. But well, it's not as bad as it sounds. There's the efficiency to consider. Like electric drivetrains, they are highly efficient, easily reaching about above 90% efficiency total, like from the battery to the traction power. Whereas with engines it's way smaller. I think jet engines are the best ones you can get, and they might reach something like 50% efficiency. Not nearly sure about that, so please don't hang me if I'm wrong, but something. Yeah, yeah, that's what I think. But anyways, the electric drivetrain is gonna be roughly twice as efficient. Okay, that's a difficult question because it depends on what you consider, what you include. Right now the batteries are gonna be huge, of course. Yes, heavy and huge, but the motor and inverter itself, their power densities are quite high even now, and what people are building and trying to build, prototyping now, they are gonna be even higher. They are easily better than most combustion engines now. They are starting to reach the power density of typical non-military jet engines now. I think maybe they have even exceeded them by now. And also another benefit is that they are mechanically so simple. Like if you consider jet engine, it's hugely complex. Well, technically you have only that one moving part there, the fan and the auto compressors and so on, but they are mechanically demanding. They are gonna be spinning at extreme speeds with very high temperatures, so on. So the construction is difficult. Compared to that, electric motors are much simpler. And because they are simpler and they can easily be smaller, you can have this kind of a distributed propulsion where you have several, like many more motors than what you have typically seen on a plane. And as far as I know, that can have some aerodynamic benefits. And of course there's the safety issue, like if you lose a motor or two, it doesn't really matter that much. You can still fly almost as easily as before. But yeah, if we return to the technology and where these electric planes could be used, at the moment the most promising target are these kind of a short and medium haul flights between some 100 up to 1000 kilometers, and that's actually where the most what the most flights are like. If you look at the total number of passenger flights taken, I think a huge share of them are very short. So they are like a prime target for electrification. And on the technology side, we are not that far away from them. We would still need some improvements in the battery technology, mainly the energy density, and then maybe a redesign of the planes to make them more aerodynamically efficient to fully utilize the possibilities offered by electrification. But if and when we are able to do that, I think it seems that short-haul, medium-haul electric flights are very well possible within the next few years or decade or so. Well, yeah, it's for like 20 or 50 passengers or so on. So not the smallest one there is, but not the biggest one either. Yes, I think even now it would be quite easy to get the plane in the air. It's just going far enough is the problem. I mean, getting enough energy to do that. But yeah, well, maybe batteries are not the only option. Well, people are speaking a lot about hydrogen fuel cells, but they are again one thing that I'm not very convinced about, because yes, indeed, they always go on about how high the energy density of hydrogen is per weight per mass. What they neglect to mention is the energy density per volume, which is not very high. So if you use like compressed hydrogen, you would need a huge tank for the plane, basically. At least for long-haul flights. Again, maybe it would be easier for short-haul, I don't know. And again, you could improve that energy density by having it cryogenic liquid hydrogen, but again, it has its own issues. Well, it's cryogenic, it's difficult, doesn't really feel that safe. Okay, another issue with fuel cells is that it's not very efficient energy-wise. I mean, there are many steps needed. You have to make the hydrogen. Ideally, you would be using electrolysis to split water into hydrogen and oxygen. Its efficiency is not that high. Then you have to either compress or liquefy the hydrogen. Again, some energy loss. And finally, the fuel cell itself won't have that high of an efficiency, usually between 40 or 50 or 60%. And again, you lose quite a lots of power. And then if you look at the combined efficiency from the power grid into propulsive power, which is the end product that you want, the combined efficiency will be quite poor. Meaning you will need to pay for more electricity compared to batteries, meaning it will be more expensive. So that's an obvious economic drawback. Another thing is that, well, I mentioned that the efficiency of fuel cells is not that high, meaning cooling them will be difficult. The waste heat, it needs to go somewhere. Getting it somewhere, well, again, you need a cooling system for that. Again, it's gonna be adding mass to the system. So on. So I'm not nearly convinced about fuel cells. Well, maybe one semi-promising approach is that I have seen is that you have a hybrid system of fuel cells and batteries. You have a rather small fuel cell that is producing the, let's say, the constant power that you need for cruising. The small power, small is, so the fuel cell can be small. And then for the takeoff, where the largest powers are needed, you have a smaller battery pack for that. So you are taking the big power out of the battery pack, and for cruising you are gonna be using the fuel cell. And that looks like semi-promising to me, but again it has that issue with the hydrogen and its volume energy density that is not too good, and all the other cost issues, so on. But let's see how things turn out. I think we will see we will definitely know much more in a few years or so. Yes, maybe the most important thing to know here is that we don't have practically any so-called green hydrogen nowadays. It's all black. It's made out of fossil fuels by some kind of a chemical reaction. So they split the hydrogen out of the fuels, like oil, gas, whatever. And as a byproduct, they have carbon dioxide and they just release it, vent it into the atmosphere. So the process is not clean at all. If you were to use that kind of a black hydrogen for propulsion, it's very bad for the environment. I think it would be simply better to just use the gas or gasoline and not bother with the hydrogen at all. And it also, in my cynical mind, it explains the push towards hydrogen as a fuel, because the fossil fuel companies, they would benefit greatly out of that, because in the short haul they would be simply selling the hydrogen that they are already producing out of their fossil stuff, and in the long run they would be able to utilize their existing infrastructure, because they definitely know how to transfer and pump fuels. Like their entire business model is built on that. It's what they do, it's what they know how to do. And simply swapping gasoline or natural gas for hydrogen wouldn't be such a big step for them. It would fit exactly within their business model and paradigm. Yeah, maybe one more thing to add is that if you used a more advanced fuel cell, like I think methanol is commonly thrown around, and that would solve many issues. Like methanol is it's a liquid at room temperature, and its energy density is almost as good as gasoline or jet fuel. So if you were able to use that would solve a lot of issues on the plane side, like where to put the fuel, how to store it, so on. But again, there are flip sides, like the technology is not ready at all, as far as I know. It's not even on the level of hydrogen fuel cells. And again, there would be the cost side to consider, because it would be even less efficient than using hydro. Yes. Because you would probably be making first hydrogen and then converting that into methanol. Unless you use some biofuels, biomethanol, which might be an option, but then again, there's the questions of, okay, if we are making biofuels, why not just use them in a conventional jet engine? But again, time will tell how it goes. It's been a nice discussion already.
So I want to say thank you to Antti. He was so kind, so professional. It was a massive honor to have him be the first guest, and to have him so qualified, just an expert in his field, come and talk to EVPM was a huge honor. Hopefully he'll be back. We'll be talking about a lot more motors. Again, just a massive honor. So grateful. Hopefully you guys also enjoyed it. I'm gonna see if I can timestamp some stuff so you can hop around. And yeah, thank you. Thank you so much. Thank you to everyone.